Welcome to Wednesday lecture of week 4. We're about to start on a topic that has everything to do with being able to kind of visualize things in 3 dimensions. So at least for this introductory video, and probably for quite a few of these other ones, I'll actually kind of be on camera here just to kind of show you some of the things that we're going to talk about on various PowerPoint and whiteboard discussions here. At least for this very first one, because everything has to do with kind of seeing things in 3 dimensions, what I've done is I've thrown together some model kits that you'll hopefully be able to see in this like little area that I've saved for kind of seeing different things. So one of the things we're going to do at the very start here is we're going to review stuff that we've already talked about in terms of isomerism. All right, and so keep in mind that that isomer word kind of means that like there is some sort of relationship between 2 different organic molecules, right? And the one that we talked quite a bit about is this idea of structural isomerism, right? And so what I've made is something that's just a simple alkane that contains 4 carbons. I put them all in a line, right? And one of the things that is true is that we could actually put these parts together and end up with a different hydrocarbon. So what I could have done is I could have taken this thing, which right now is in 4 carbons in a row, and instead of having like a little methyl group out at the end here, I could switch this methyl group over, take the position of one of these little white hydrogens right here, and we found that that would actually be a structural isomer. Keep in mind, a structural isomer means that you have the exact same molecular formula, just a slightly different connectivity pattern, right? And so let me do that right now. And so here you'll notice that it's fairly obvious that we no longer have 4 carbons all in a line, right? So this thing is actually named as a propane. This is an example of 2-methylpropane, right? But we called this a structural isomer, right? And those 2 are related in that they're made up of the same things, but they have totally different physical properties, totally different chemical properties, and things like that. Another type of isomerism that we talked about was geometrical isomerism, and the most common place that you see that is with a certain type of alkene or a certain type of double bond. And so a good example of that one is right here. So I just kind of, those red spheres just kind of represent, whatever you want them to represent, and the white spheres represent all the hydrogens. But what you notice here is because I have some sort of restricted rotation about that double bond, is that I can't twist this, right? These 2 red spheres are on the same side of the double bond, and a geometric isomer of that thing might look like this, right? Where we have something where those red spheres are on opposite sides of a double bond. And this was a little bit more special than a structural isomer, right? The structural isomer is something that is something that, you kind of pluck a group off and put it on again. Just like this one, I could interconvert a cis isomer into a trans isomer by doing that kind of thing. But, you can kind of imagine living like these red spheres, and you can kind of imagine, okay, what kind of neighbors do I see, right? Well, I see a single carbon neighbor there. I'm right next to another hydrogen down here, and I kind of look across my double bond and I see a white sphere there, right? And so this guy and this guy, right, if I take a look at that same kind of environment on the cis, you notice that I have a red sphere that's on the same side as another red sphere, right? And so like you can kind of see that like kind of how to like disconnect all this stuff, put it all back together. But what we're going to talk today is a little bit more subtle than that, right? What we're going to talk about today is something called chirality. So we're going to talk a little bit about what it means to be chiral and how it relates just real briefly to an organic chemistry context. So let's first define what chirality is, and then we'll relate it directly to organic chemistry, at least kind of an introduction to the idea. So it turns out that the world around us, especially we as human beings, live in a world that is chiral, right? And what is chirality? Well, it comes from a Greek word that is talking about handedness, right? And so if I take a look at both of my hands, right? Here we go. I've got a hand here, and I've got a hand here, right? So looking at my hands, you'll notice that there's a certain symmetry to them, right? That symmetry is that, right? If I kind of put a reflection plane through these two things, one kind of interconverts into the other, right? And so in other words, we have what's called bilateral symmetry here, right? And so the weird thing is, though, it is not true that my right hand is the same as my left hand. Yes, they are symmetric, but if I try to take my right hand and put it over my left hand, what I end up with are mirror images that are not superimposable, right? So when you say mirror images that are not superimposable, it turns out that is the definition of something that is chiral, right? So my right hand is chiral, my left hand is chiral, and there's a special relationship between them in that they are both non-superimposable mirror images of one another, right? I make a mirror image of my left hand, I turn out with my right hand, but those things are not superimposable, right? In other words, like my thumb is kind of on the wrong side if I do that, okay? It turns out that any carbon center that is bonded to 4 different things, right? Keep in mind, carbons are bonded 4 times, but if those things are all different, it is very likely that you're looking at something which is also chiral, right? And so I've got a couple of like kind of mini activities that'll help you kind of see this in just a second. But what I have here is just a simple carbon that I bonded to 4 different things, right? And what I did is I kind of held that in place. Something like this. I'm sorry, I'm really bad with this, having everything being backwards. And what I did is I made its mirror image, which I'll hold up over here. There it is, right? Well, that's not held properly. Let's hold it to your perspective properly. Okay. So what I have is, I'll try to convince you, this is so hard to do, is that I have 2 things that are, in fact, mirror images of one another, right? But they do not superimpose. So let's see if I can hold these in such a way that you can kind of see that, right? One is the mirror image of the other, just like my hands were. But then if I try to kind of bring them together, no matter what I do, those green spheres are kind of on the wrong side. Or I could try to match up, let's say, all the green and blues. And what you'll notice is that now the red and the whites are kind of on the wrong side. It turns out that this kind of handed thing happens all the time in the human body. The reason that, organic chemistry kind of came to be is because it was the chemistry of, life, basically, when it came right down to it. And it turns out that, like, for instance, if we're going to make a drug to interact with a human being, you have to make sure that you have a good understanding of what kind of chirality is in the body, right? So the analogy I kind of used to understand this idea that we have to, be conscious of the fact that we are chiral beings is probably best exemplified by me putting on a pair of gloves, right? So I brought some like really nasty looking work gloves that I've been shoveling a bunch of compost with, so it smells delicious. But, I've got my hands. I know that those things are chiral. And I have my really gross gloves here, right? And so, if I have a right hand and I would like to put on a glove, I can put on this right-handed glove and everything is awesome, right? In much the same way as that if I design a drug with the right chirality, it is going to interact with the enzymes quite nicely, right? Just like, I guess in this model, my glove is an enzyme. Well, what happens if I try to use let's say that I have some sort of enzyme that is the opposite handedness, and I try to put my right hand in it. Well, it's kind of like the same thing as using this, left-handed glove on my right hand. Well, I can do this. That doesn't fit right. Or I can flip this sucker around, but you'll notice it doesn't look right, right? So here's what the glove kind of does. Like all the fingers are articulated differently, and it looks like I have a hole in my glove. Time to get a new glove. But you can tell that I really have to pay attention to make sure that I use the proper chirality. And in much the same way, we have to make sure that in organic chemistry, we are able to kind of recognize this thing. So in the next couple of lectures, I'm going to slow down just a little bit just because this is kind of getting into something I really struggled with. Like, it's really hard to kind of have spatial awareness and 3 dimensions, and what does it mean to have a molecule that is chiral? So I'm going to try to, where I can, kind of explain some of these concepts with lots of demonstrations. And we'll see how it goes. The important thing to recognize is that at least at this point, when you talk about chirality in an organic chemistry context, it really results from a carbon that is bonded to 4 different things. And before I let you guys go, what I wanted to do was take a carbon that's not bonded to 4 different things and show you why it is not chiral in that case. So bear with me. Okay, so what I've done is I have just kind of randomly taken one of the colors off, and I made sure to use the same color as another one of my groups. In this case, I picked out the white, right? So you can see the fact that this thing is no longer a carbon bonded to 4 different things, okay? What I did is I also made its mirror image, right? So these are both mirror images. Notice that both of these guys have hydrogens. And so the real test for chirality, it turns out, isn't just enough to have mirror images, but you must have non-superimposable mirror images. In other words, there must be no rotation that I can do with this guy to turn it into what I'm holding in my other hand, right? And so this is a case that is called achiral. These 2 compounds do not have a chirality. In other words, they are achiral, right? So we've got this guy, and I've got his mirror image, which is this guy. Oop, geez. Mirror image, which is this guy. And what you'll notice is if I just rotate this, that they now superimpose perfectly. Like all the different groups are all matched up, right? So in this case, this is an example of something that has, well, of course, everything has a mirror image, right? There it is. But because they are superimposable, these things are now called achiral, not chiral, in other words. Whereas before, when we had a carbon bonded to 4 different things, that was something which is almost always chiral. There are, of course, exceptions to every darn thing, but let's talk about the 95% of the world that can get us some points on the board. So this topic, this is called stereoisomerism. Right? And there's a whole bunch of different relationships we're going to have to talk about, all that kind of depend on you guys being able to see things in 3 dimensions, which is really tough, something I always really struggled with. Strangely, it always seemed that the artists in the classes where I teach this end up being really good at seeing relationships. I was horrible. So what I'm going to do is I'm going to show you kind of Seanisms that I just kind of invented to kind of get me through this. Of course, now I've played around with these model kits so much that I can kind of see it a little better, but it was not at all natural to me. So one other vocabulary word before we go, I don't think I've used it yet. Anytime you have a carbon that is bonded to 4 different things, that is called an asymmetric carbon, right? So this is not an asymmetric carbon. This is what's called a symmetric carbon, right? So to make this thing asymmetric, keep in mind, I have to have 4 different groups bonded. So I'm going to take any one of these white spheres and replace them with a different color, right? And so now this thing is called an asymmetric carbon. And so what we're going to do is, as we kind of talk about this, we're going to kind of build on these different asymmetric carbons, and we'll talk about some relationships that are special with this handed thing. We'll make it kind of one step more complicated. I'll put an additional asymmetric carbon on there, and then eventually what we'll hopefully end with this idea of having you know, like a huge protein that has bazillions of different chiral carbons, that has a whole bunch of different relationships that you can talk about, all of which you have to match if you want to truly kind of understand the chemistry of life. Yeah, that sounds easy.